Alright guys, hello again. So this time we will be studying project 1 part 3, and the contents are like we will learn how to start layout, and then we'll discuss about layers like metal layer, polysilicon layer, and the ground floor. I call it ground floor, which is the substrate. And then we will also discuss a little bit about lambda rules, and then this is DRC is actually a design rule check. So basically these two goes together, and then what we will do is we will extract our layout, which will give information about the sizes and capacitances and everything in a very in a way that other simulator can use. And this is LVS. So in this step what we will do is we will connect our layout design with our schematic, and then we will check like if our layout is okay, or is it the same as the schematic we created. Alright, let's get started. Okay, here is our library manager. Go to file, new, cell view, tutorial. Okay, select layout, and here I will name it CMOS inverter layout. So I will going to make layout for 1 inverter, and you have to make layout for 7 inverter, and goal here for everyone is to make as compact as possible. So whoever gets like very compact design will get very good grade. So it's a relative grading. Yeah. Okay, click OK. Yes, yes. Okay, so here I can write relative grading, make it compact. Less area, good, less area, high grades. How does that sound? Okay, where were we? Yeah, here. Okay, so this is how layout window should look, and what we will do at first, we'll go to options, display, and then we will change some parameters. Here put 0.1, then measure spacing 0.2, then snap 0.1, x snap, y snap 0.1. so that defines the distance between one dot to another dot. Yeah, that's it. So we'll say OK, and you can zoom in, zoom out, whatever. Yeah. Okay, so let's say so in background I'm downloading one PDF. Okay, so first of all you should get familiar with lambda rule. Just Google it and spend some time, like about 10 minutes, and see what it is. So lambda is the minimum feature size of any technology design, and the one which we are using is 100 nanometer. So everything is defined in terms of lambda. Whatever the size of transistor is 2 lambda, width of the transistor is 3 lambda, like that. Okay, so in this window here are the layers. Oops, this laptop is very slow. Okay, so P-val, N-val, active, I don't know, T active. So the layers that we are going to use are N well, N active, P active, N select, P select, poly, metal 1. So these are the layers, and metal 2 if you want to use it. Okay. So how to do? So first, if I want to create a NMOS, then what I need is N region and polysilicon in the middle. So I will just start N active. N active is called N region. This is very slow. Yeah. So now you have to press R. R means rectangle. Create rectangle. Click at one point and then just drag it here. So I have created N region. Now I want to create poly. So click on poly. You can press R or whatever you like. Then this is my polysilicon. Okay, what if I put polysilicon like here? Okay, so what happened is, here is, you can call it a substrate, and sorry, not substrate, source, and this is drain, and this is your gate terminal. Okay, and now I can check if it is like valid design or not. So go to verify, go to DRC, and then do OK. If it is wrong, then something will appear. Okay, something is wrong. So go to verify, go to markers and explain. Okay, so why did we do that? So this white line and white cross is called marker. Marker means some error. Then we click on that white line, and then it will explain what the white markers are about. So there are two problems, there is one problem, which is active must be inside the select. Okay, yeah, we know that. But so this is how you can do your design rule check, that whether your design, whatever you are making, is okay or not. So this is not possible. So how can we, what is select, or what is that under the select region? So select is here. So whenever you want to create N region or P region, it should be under N select or P select. So first we need to have N select, and then we can, like, not then, but inside N select, this N region should be there. So what we will do is select N select and then press R. R means to create rectangle. Okay, hide. Then we'll do this. Okay, so this is really a transparent layer. It will just create a border. That means this area is N select. Under that you can create this NMOS. Okay, so now we will do again. Let's say if it is okay or not. DRC. Okay. Okay, so here you can, like, you can see no error, but here there is error. This something white line is here. So here comes lambda rule. So lambda rule is that whenever you select, whenever you create this N active region, you should put it inside this N select, but the distance between N active region and N select border line should be minimum 2 lambda. 2 lambda means 1, 2. So here it is only 1, here it is 2. So here no error, but this side and this side it is error. And you can see, even we can go here and like marker, explain, like this. Select overlap of active 0.2 micrometer. This is minimum. This should be there. 0.2 micrometer matlab, oh sorry, yeah, that means 200 nanometer. Okay, so what we will do is, we will make this N select area larger. How can we do that? So we can stretch it, like press of, let's get rid of these markers first. So what will go is verify markers, delete them all. We'll create all. You can select that what markers you want to delete and what markers you want to keep. At this point I don't want any markers, so I can select all and then OK. So those two markers are gone. Now I can make this region larger. Okay, so I will press S. S means stretch. I want to stretch it, and you can select whole bunch of options here as you like, and then I will hover my like cursor over here, and you can see this yellow dot line appears. That means I can click once, then I can go make it as long as I want. So I will go like minimum feature size, which is 2 lambda. What happened? Okay, yeah. Then also with the bottom one. Okay, now let's check DRC error. Okay, no error. Okay, so that is how we use DRC every time. So now onwards I will just let you know what to do, what not to do, and in the middle if I need, then only I use the DRC, otherwise I will just move on. Okay, so we have created this NMOS here, but that's not it. I want this to be a little bit bigger, so I will stretch this right here. Okay, I can make this circuit as big as I want, but in your case, like first try to make it just make it working, and then you can make it compact. Okay, so this is NMOS. Okay, what the next thing is we have to do is we have this N region here and here. So I need to connect this N region which is on substrate. I want to connect it to metal layer, so metal 1. So first I need to connect contact, it is called contact, and from metal 1 to metal 2 is called via. So I want to create a contact, so contact is CC, this is CC, and the rule for CC is it should be 2 lambda by 2 lambda, that is minimum size. So I will press AR, it should be minimum 2 lambda by 2 lambda. So I will zoom on here. So I think this is 2 lambda. You can see this big dot and then another big dot is 2 lambda. So I can click here, I can click again here. So this whole square, its color is black. It's not just it removed the N region, but it's black, so we are overlapping it. Okay, one more contact here, yeah. And then what happens if your N region is very close to this? Let's say, let me make it smaller, stretch, go here, escape, click on this one, S, enter, yeah, let's make it that, escape, click, okay. So you can see this N region is very small, and I just put this contact at the boundary of N region. Let's check DRC, where is it? This is very slow. Okay, so you can see there is a marker here, and I don't know if you notice there is one white line over here, it ends here, you can see, and there is one square over here also. Oops, there is one square over here, like marker here. So let's go to verify, markers, explain, and explain. So basically these are many errors. I will just let you know how. So whenever you create a contact, you should have at least one lambda spacing around it. So you cannot put it at border. So ultimately we have to do is stretch this thing, hide, and stretch it to 1. So now it should work. That is the main thing. And another that here you can see is problematic, because like you have n region here, you have metal pillars, that these are the contacts, and then you have nothing on top. So actually you, this black region, the pillars, you have to connect to metal one. So what I can do is select metal one, select rectangle, and also the metal covering should be large enough, like 1 lambda large enough than the square contact. So now the error should disappear from here. Also this error, that the boundary error was coming, that it is too much close, it should also disappear. These are the basic errors, and that is why I am going little bit in depth in this. Okay, so you can see this area is okay, but this area is still not okay. Why? Because we don't have metal layer on top of this. So I can connect metal layer, metal R contact, and here, oops, what happened? Oh god. Okay, yeah, anyway the error will go. Okay, there is one error over here. Actually I shifted this thing. Let's make it small, stretch, enter, small, yep, even you can make it more smaller, make it small. Okay, now I will create a PMOS. So creating PMOS is tricky part. So you need to create an well, and for an well is here. Let's see, you have to create a big enough an well. I think the lambda rule is like you have to create big area which has 6 lambda by 6 lambda, or like extra region. Maybe we'll see the errors anyway. So this is an well, let's say, and inside an well what we will do is we will create P active region, but before we can put P active we need to have P select. So we'll select P select. So let's say this is my P select region. What I can do now is I can put P active region inside, and make sure you have a boundary also, like 2 lambda boundary. Okay, now what I can do is I can put a polysilicon over here, but I will align this with this, so that way it is more like it will look good and it is good layout design. So I will do just, I will select everything, just shift it little bit like that. Yep, and then I can extend this poly by using S, I guess, hide, that's tricky part. Okay, I got it. Huh. Oh God. Okay, yep. Now I have created that. Now I can create, actually I want to put this thing closer, escape. Yeah, why, you will know soon. You have to click outside sometimes and inside and blah 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 to select this. Okay, now same thing. Okay, so the best part is you can select this, press shift this and that and that. So I have selected 4 items. I can press C, I can click on them again, very slow. So now I can go up here, I can paste them here. Okay, so best part is this, copy paste. Okay, now let's say this is PMOS, this is my drain, oh this is my source, this is my drain, this is drain and this is source. So I have to connect these two via metal layer. So I can do that by zoom in, or you can say use metal one layer, then rectangle, hide. Okay, so this is, everything is connected. So one thing to know here is, suppose I am creating this metal layer, metal wire here and another wire here, this one. So here you can see this boundary, but they are connected. Actually there is nothing like fine line, nothing like that. This will behave same way as like this. This will behave same way. And there is also metal one layer to metal one layer lambda rule, that how far you can put 2 metal layers. And I think, I don't know, like 3 lambda, 4 lambda, this is right now 2 lambda distance, this is called 1 lambda distance. But you will know, if you put 2 metal layers so close, then it will show in your DRC check. So don't worry about that. So basically you can put some pieces together and that will act as same. So don't worry about that. So close it, delete, and here, okay. So what we did here is, we have this metal portion coming outside, which will act as VDD, then this is middle portion and this is ground, okay, and this is our input. But polysilicon is not connected to anything. So we have to connect polysilicon to metal layer 1. Everything that comes out of the circuit should be connected to metal. So what we can do is, we can extend this polysilicon. We'll see what happens. Let's see. So I want to put a contact on this poly. So I have this contact. I will create rectangle here. I think we will see many DRC error because this is so close. You will know what I mean. Okay, so first of all we need polysilicon around it. It is not possible this way. And why I created in the middle? Because I want to keep 1 lambda distance around it. So I will put some more polysilicon here, just as much as I need, not some more. So I have created, oh, now we have a problem. if I create a metal square here, it will definitely connect with this. So two things, I can extend this over here and then create a metal here. Let's say stretch. So I am making this design and making so many errors because that way you get to know that what to do. Otherwise I can make this circuit a very big and there will be no DRC error, but then you will not know, like if you are trying to make it small, then you will face some errors. Okay, now metal one, rectangle. Very slow. Okay, let's check for errors. I think we will get some. So many errors. So first of all, some errors are here. This says this contact cannot be so close to this polysilicon. I think that's it, that is that 100%. Markers, explain. Active contact to transistor gate spacing is 200 nanometer and metal one spacing is 3 lambda. Oh yeah. Okay, so this contact should go 2 lambda. So 1 to the left, this is 1 to the right. Okay, let's make it that way. Okay, so what I will do is, even here it is the same problem. I will make it select, shift, press shift and then click everything, select everything, select everything. Now move it 1 lambda right. What? Not that far. This is 1 lambda. Okay, now perfect. But here we have a problem. We'll solve it later on. Okay, select, shift, select, shift, select, select. Make it 1 lambda here. But you see the problem, right? What is the problem? This orange area should be more than that. So press S. Orange area is, orange is P active, should be larger. Okay, here it is okay. Here this green area should be larger. Okay, and then I think this error will appear because this P select is 2 lambda spacing, but we have here 1 lambda. So I will make this big also. Okay, now you can see this big marker over here, and that marker is because earlier I told you that there should be some spacing in N well. Okay, so let's see what is that spacing. Explain this marker. It says 6, yeah, 6 lambda. So you should, the boundary of the N well should be 6 lambda away from the active region. So this is how many lambda? This boundary is orange. Orange boundary is here, green boundary is here. So this is 4 lambda. 1, 2, 3, 4. We have to make it big. We have to make it 6 lambda. So stretch is very useful. This is, we stretch this 6. How much here? Here 6. Okay, we will have problem here. If you make this thing 6, and problem is it is very close to this. Well, let's see. So you have problems everywhere. Oh, no error. Alright, so this is our inverter final. So now let's give it a, oh no, not yet. So how many, let's say suppose this region is NMOS. Suppose this region is NMOS. So how many connections does any particular NMOS have? 4. What are those? Source, drain, gate and substrate. So here we have drain, here we have source, the middle is gate which we are connected, but we don't have substrate. What is substrate? Substrate means this is N region, but outside of this N region, which is you can see the black region, is P substrate. So we have to connect P substrate to metal layer and to ground, and ground is this blue metal. Okay, so what we will do is we will connect P substrate to metal layer 1. So we will connect this contact, like suppose this is P substrate, right? So we can, oops, R, enter, we can make this contact here, but this won't work. Why? Because you need a P active region beneath it. So we will delete this thing, delete, we need P active, but for P active you need P select. So we will first do P select. So we will do, okay, so what I can do is I can put that connection anywhere in this whole circuit, anywhere, that will run exactly same. But to reduce the size, what I will do is I can put as close as possible. This is N select area, and inside N select I can do only N active region, but outside N select I can do P active region, but for that I need P select. So I will create a P select region over here, R, enter, this is P select, let's say U, make it big, P select. Okay, what I can do is now I want to P active region, let's say P active region, oops, escape, R, enter, this is let's say P active region. You can make it small. Now I can make contact CC in the middle. Okay, now I can put metal layer on it, on top of it. Okay, so I am putting metal layer, but what I can do is this is going to be connected to ground with this thing. So I will do this. So this both of them are connected to ground. So what I am talking about, let's see, CMOS inverter, image, go to image, which one, this one, oh wow, one is that and one is here, let's say. So here this source is connected to ground and this substrate is connected to ground, that means both of them should be connected at some level. And here, yeah, it is, you see this is NMOS, N source and drain, and this is gate. So N source is connected to metal layer 1, here is metal layer 1, and here is tap, this is called actually tap. Tap means P substrate also connected to ground. So P substrate, and this black region here is actually P type P dop like region, but it is highly P dop region, and the doping concentration will be same as this region, P drain. Yeah, so both of them are connected together at higher level. So this is what we did, like we connected them together. Okay, the same thing should happen over here. So this is P well, oh yes, where it is, this is P well, and you can see N mod is, oh not P well, this is N well, and the N well should also connected to VDD. So we need to create another tap over here at the edge of N well, and we should connect it to VDD. So we need another contact here and one metal layer here, and for that we need an active region over here. So we will do that. So we will do an active region here. This is okay. To make an active region here, we need an select. So we will select and select, and then we will make it R. Okay, and select. This is my and select. Let's say U, and we will need to make an active region under it, and active, but you know the boundary to the n select and n active should be 2 lambda. So I can make like here. So for that I need to make these things bigger. So first I will stretch it as enter. Let's make it big, whatever. Yeah, now I can make an active R, enter, 2 lambda space, make a square, make a contact at them like at the center, then metal 1, and I can do metal 1, connect it with this. So this is connected to VDD. Okay, what we did we just did is this black region is N type region, and this is called contact, and then this horizontal line is called metal 1. Yeah, like this. Don't we have a good images? Layout, let's say layout. This one. Okay, where is it? Yep, this region is P plus inside N well, and then this is N region. You see, N plus is hash and P plus is solid. So this is N plus, P plus, here N plus, but this is P plus, and this vertical pillar is called contact, and the horizontal line is called metal layer. Okay, anyway, go back here. So here the things are complete. DRC check, no error. Oh, there is one error. Okay, what are these errors? This contact should not be this much close, I think. How many lambda? 1, 2, 3. It should be 4 lambda minimum. Let's find out. Verify, marker, explain this. Active of different implant spacing 4 lambda. Active contact to active spacing is 5 lambda. So this is contact and this is active. This should be 5 lambda. Okay, let's make it 5 lambda then. How do we make it? We select them. Let's just clear our marker. What? Why can't I select this thing? What is wrong with this? Close window, escape, escape, escape. Yeah, shift, shift. Okay, I want to move it away. 5 lambda. Let's make it this far. Okay, so what happened? We just need extra stretch, enter. Need to stretch this metal there. Is it 5 lambda now? 1, 2, 3, 4, 5. Yep. Let's see. Okay. Yep, no error. Okay, so our inverter layout is complete. So what we have to do is we have to name it. Okay, let's name it. So first, while giving name, you have to see what the names that you have used in your schematic. So let's open the schematic first. Where is it? Here, library, oops, library inverter with symbol. This is with symbol. And schematic, oh yes, this is schematic. You can see it is locked, so I have to open it. Inverter with symbol, tutorial library with symbol, schematic. Delete this to lock files, enter, come to library. Okay, now go away, yep. Okay, let's see what are the pin names. VDD exclamation, ground exclamation, inverter out, inverter in. All right. So which is in? This one. This metal point is inverter in. So you can go to create pin. Terminal name is inv_in. Okay, here is the thing. Create a label. Click on create label. Then go to options. Then make it very small. This is 1, that means 1 micrometer big. So it will be big from here to here, very big. So make it 0.1 and everything is okay. Click hide. Now actually, like as in schematic, you just have like the pin shape automatically appear, but in this case you have to make the pin. So what I will do is I will make this, oops, escape. Okay, so you are connecting pins to metal 1 layer. So actually you can select, you have to select metal 1 or wherever you want to create a pin, at what level, then select metal 1, then go to create, go to pin, give it a name, select this create label. Okay, and then just like you can do this square, and now that pin is connected to where? You can put it anywhere, this label. Okay, like that. So this is inverter in. These two are linked, so it's not like pin is here, whatever. Escape, again another pin, create pin, and oh, actually you have to see this is in out. Actually the output inv_out. Click OK, hide. Where is out? This is output, let's say, and then you can put it anywhere. This is in out. So basically the problem here was select this pin, this is pin, select Q, Q means property, and go to connectivity. It was in out, nope, it is input, then OK. Now I need to connect with VDD. VDD is here, so go to create pin, VDD exclamation mark, and make it input output. You can even take any shape, circle, polygon, whatever. This is your pin, VDD, make it here so you can see it. Now I need to connect another pin, ground, where create pin GND, make it input output, and then here this is my ground. Yep, so everything is complete. Now I will save it. For last time I will verify it. No problem. And even you can see here, or two errors. Where are these two errors? Active enclosure of gate 0.3 micrometer. Oh, I know where it is. It is here. You see this white line here, if you can notice. So actually, whenever you create a polysilicon, this red region, it should extend more to some in a space whenever you create. So here I did not extend, so here I need to extend, that means stretch. Okay, stretch it, done. Go to verify, DRC error. Okay, let's see any, zero error. Yep. Okay, so now this is DRC. Second step you will have to do is extract. Go to extract, select the switches, select two switch, press shift, hold and press shift to shift, and then select these two, then click OK. This is extractor. Then all you have to do is OK. It will create a directory, and you can see if it is successful. Like if it was not successful, there's something appear, and it is here extracted. You can see here, go up, inverter CMOS layout, nope, refresh, yep, extracted. Here this is extracted files, and then okay. So now what we will do is, we have designed a layout for this circuit. Now let's see if that is correct or not. So what we will do is, go to this layout. Okay, let's see what is length and what is width. So length of this transistor is the width of polysilicon. The width of polysilicon is here from 1 lambda, 2 lambda. 2 lambda means 200 nanometer. So this is called width. Sorry, this is called length of this transistor, because electrons will travel from this region to this region, or whatever, from reverse, under the polysilicon, and the polysilicon is wide, how much wide is 2 lambda. Okay, that means 200 nanometer, and this vertical is called the width of the transistor, and that width is currently, let's say 2, 3, 4, 5 and 6. It's a 6 lambda, so 600 nanometer wide. Which transistor? PMOS. What about NMOS? NMOS is also 600 nanometer wide. So here we have like both same size, so that is fine for your circuit. Just try to make it compact. Okay, so now next thing is, but in schematic we have different sizes. So actually when you connect like correlate schematic with layout, this sizing, they will not count it. They will just see that if the transistors are perfectly matching or not. Okay, so now what we will do is, we will save this and go to verify. This is LVS. We select LVS, come here. What is LVS? I forgot. Layout, extraction and verification. Fancy name. Okay, this is layout. Oops, this is layout. This is okay. So what we have to do is, we have to select create a netlist schematic. You have to specify which schematic you want to connect it with. So, go to browse, select library, select the schematic you want to connect it with, and then select schematic, not the symbol, schematic. This is the schematic. Then close it. Then which the extracted file you want to connect with this. So, this you do not have to select this layout file, you have to select the extracted version of this layout. Go to browse, select the library and select the layout, and then you will see that there is a layout file and there is extracted file. Extracted file should look like this, layout should look like this. This is just what we created here, extracted. Then close it. So, you can see both of them appeared here. Now, what it will do is it will correlate, and what you can do is run and wait. Are you supposed to wait or what? Oh, it started. So, it is working in background, we have to wait. Yep, the LVS job has completed. Netlist match. Bingo. Close. How do you know if it is match? Minimize. Go to click on output. This is sweet little thing. Maximize it. See. Netlist summary for blah 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 blah. 4 nets, 4 terminals, 1 PMOS, 1 NMOS. Netlist summary for blah 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 blah. Terminal correspondence points, these many, and unmatched 0, rewired 0, size errors 0, active blah 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 blah. So, where like if there was a problem you could see, but there is no problem. So, everything is okay, everything is matched. So, I will close this window, and this is output. Run we did, okay. Then close this window, okay. What you have to submit? You have to submit screenshot of this. Remember, screenshot of layout, screenshot of your schematic, and then like you have to measure the dimension of this thing. How to measure the dimension? Press K. K means create ruler, and select here, where is it, snap target none, make the snap target none, then hide. Then you can select from click from the here to here. So, this shows that this length is from 0 to 3.2 micrometer. This is, and then I want to know the width of this from here to here. It is 3.4. So, 3.2 multiplied by 3.4, whatever, 9, 10 something. So, the area of this region is 10. You can see I am measuring from here to here. So, my marker is away, but I am measuring the compact size, whatever the compact is. So, what you have to submit is the screenshot of this the layout with marker, with this marker. Now, you can take a screenshot, and many people do not know how to like make a screenshot. So, actually when you make a screenshot, do not worry about how it looks, just submit whole screenshot. Okay. So, that is it about creating layout. So, what you have to submit is screenshot of this, screenshot of this circuit, and a file. Which file? So, go to go to back, okay, now refresh, go back, refresh, and you will see this LVS. Where it is? It's right outside in your folder, just beside the library. Okay, how did that happen? So when you select, oops, escape, when you select LVS, so every time you make a layout for another circuit or whatever, you have to select this run directory. So I have selected LVS. If I have selected, let's say, tutorial, let's say LVS for tutorial, and then run. Check and save, modified, yup. Okay, see, the job is completed. Now close it. That was in the middle because I click at something and that error, like that pop-up appeared, but it was nothing. Okay, now I refresh this and you can see this LVS appeared. So now go to that folder, go to si.log, and you should see this log file. What is match or whatever, and also si.out. Okay, so you have to submit si.out file, si.out, that's it. And when you create, like you already created the schematic, suppose 7 inverters. Do I have 7 inverters? Let's see. Where was it? I created 7 inverters for you guys. Nope. Let's say, okay, let's say you had this circuit like this. Shift C. You had this circuit like this, wire, enter, oh god, yep. So what you have to do is remove these power sources, or you can create another schematic. Like suppose this is your schematic, whatever you have, right? Just check and save it, and then go to new. This is blank, brand new schematic, and just name it that new 7 inverter schematic for layout, then new tab. Okay, so and what you can do is just select everything, press C and copy it and put here. Oh, this is layout. Oh god, I accidentally created layout. Oops, just close this, make a new. You have to select here what schematic, be careful, then okay. Now here you can put it. Okay, so remove everything, remove every power source and everything, and you have to do is click this, delete, and you have to put, suppose whatever name you give in, suppose you give it a label. No, now you don't have to use label, you have to use pin. So create pin, let us say input inv underscore in, and then connect it input pin inv underscore out, select output mode, okay, and go here. Okay, but if you made a symbol like this, but you don't have, like you cannot see where is ground and VDD, so you have to create wire, enter, suppose like this, and another wire, then escape, pin GND like this, oh escape, pin GND, make it in out, hide, yep, and then pin VDD, yep, and then in out. Okay, I think well, check it out for yourself that you need these wires or not. I don't know, I think we don't need it, but you can put it for safety. So actually there should not be any power sources in this, so you can use this like this. You have 7 inverters here, and then select this schematic when you do LVS, like when you do LVS schematic, select that schematic right here, not here, here, sorry. Alright, so your goal is to make this thing as minimum as possible, as minimum as possible. Okay, that's it for the day. Thank you very much.